Okay, so the first thing that I want you to learn are element symbols, but an element symbol is not a pure substance, it's just a symbol for an element. And then if it's a substance, it would have a chemical formula. And so a chemical formula and an element symbol are not the same thing. A chemical formula represents either an element in element form, like this silicon is in element form. Okay. And if I put Si, I wouldn't mean that Si on the table, I would mean an actual sample of silicon. Those are two different things. And so all an element symbol does is it represents an element. That's all it does. It just lets you know that there's that element and you're talking about that element. Chemical formula, it represents the makeup of a pure substance. And each pure substance has a chemical formula. And so elements and compounds. So this is where it can kind of get confusing because there's the word element and there's the word element, but they don't mean the same thing. When we're talking about just element symbols, we're not talking about an actual substance. We're just saying, what is the symbol for nitrogen? And you would say N. And what is the symbol for silicon? And it's Si. And what is the symbol for sodium? And you'd say Na. We're not talking about an actual sample of sodium or silicon or nitrogen. The chemical formula, what it does is it lets you know how many atoms of each element there are in the chemical or the molecule. Or it could just be a ratio. It's a 1-to-1 ratio or a 1-to-2 ratio. So I'm just going to take an example of an element. So we're just going to say oxygen. What is the element symbol for oxygen? O. But if I asked you, what is the chemical formula for oxygen? I'm not talking about the symbol oxygen. I'm talking about oxygen in its element form that you need to breathe. So when you breathe in, one of the components of air is oxygen. Does anybody know the chemical formula of the oxygen that you are breathing in air? You know? It is O2. Elemental oxygen is O2. And so a symbol doesn't mean element form, it just means atoms that have that many protons. That's all it means. So if we want to talk about the element form of oxygen, it's O2. Yes. Okay, so O2, what that means, when you have a chemical formula, you have symbols and you have subscripts. And the subscript will come directly after the element that it belongs with. And that means that you have two of that element, two atoms of that element. So you got two oxygen atoms. You can also have compounds that have oxygen represented, and you would see the symbol O. And so the symbol just lets you recognize what elements are in the element, so what element it is, or if that element is in a compound. But oxygen in O2 is different than oxygen in compounds. And so some compounds that contain oxygen are water, carbon dioxide, and silicon dioxide. So each of those are compounds that have oxygen in them. And how do we know they have oxygen in them? because there is a symbol O in each one of them. Okay. So in a formula, if it's a compound, by definition, back from the pure substances stuff, a compound is something that contains two or more different elements, and there is a number or a defined ratio or a set number. And so that means there's two hydrogens and one oxygen. There's one carbon and two oxygens. These are set numbers. So H2O really is two hydrogens and one oxygen. And carbon dioxide really is one carbon and two oxygens. Silicon dioxide, though, is a ratio. And so in silicon dioxide, there is one silicon for every two oxygens. But with water, there actually are two hydrogens and one oxygen. And for carbon dioxide, there actually is one carbon and two oxygens. And for oxygen, the element form, there are two atoms of oxygen. So the chemical formula either gives you the actual numbers or a ratio. And the only way that you know this, whether it's a ratio or actual numbers, is we have to get into, is it a covalent molecule, or is it an ionic compound, or is it a metalloid non-metal network? That's all like later on, that's not right now. But if it is a set number, then we can draw something called the structural formula, or you can look at the structural formula. You're going to learn how to draw these in a few weeks. So there's also something called the structural formula. And it's similar to chemical formula because it shows the makeup of the chemical, but it actually also shows the structure. And so the structural formula actually shows the bonds and arrangement of atoms. In a molecule. So if you look at O2, H2O, and CO2, you don't know how it's bonded together. It looks, the way it's written, it looks like there's two hydrogens together and then an oxygen. And the way carbon dioxide is written, it looks like there's a carbon and then there's two oxygens. But really that's not the way it's organized. It's written so that the same elements are kind of grouped together and then a subscript tells you how many. It's not how it's bonded. And so what I want you to be able to do right now is to be able to look at a structure and say, that's the symbol for this element and there's this many of them. And then that's the symbol for this element and there's this many of them. And write it as a formula. So every number would be a subscript for that element. And so for these three things that are molecules, this one's not a molecule, so I can't draw that one. But for oxygen, the O2 means there's two oxygens. And there has to be a bond between them to have it be in the same molecule. So that is a representation, a structural formula representation of O2. So O and O are two O element symbols. And then there's what looks like an equal mark between them, but does anybody know what the equal mark is? it's really a double bond. A line between two atoms is a covalent bond, and if there's two lines between the same two atoms, it's a double bond, a double covalent bond. And then I put some dots, and the dots represent electrons that are not being shared with the other oxygen. So carbon dioxide, it looks kind of like this one, but there's a carbon in the center. And so carbon's in the middle, and there's an oxygen on one side, and there's an oxygen on the other side. And so the carbon in the middle has a double bond to one oxygen and then a double bond to the other oxygen. But if you look at it, what I want you to be able to do is not draw that, okay? I want you to be able to look at that and say, how many carbons are there? There's one, so I write C. How many oxygens? 2, so you write O2. And then water, oxygen's in the middle, and hydrogen's on either side, and there's just a single bond, and then oxygen has some dots on it. And so you can see that there are 2 hydrogens, that's the H2, and then 1 oxygen, the O. If you notice, all the oxygens I drew have 4 dots on them and 2 bonds. There's like a trend there. So when oxygen forms bonds, it forms 2 bonds, and it has 4 dots. Yes? Uh-huh. No, and it's because it's a ratio. So if you were to Google silicon dioxide, one incorrect drawing would look just like carbon dioxide, but it would have silicon in the middle. But if that was actually the structure, then silicon dioxide would have properties very similar to carbon dioxide, which would mean it'd be a gas or a really low boiling liquid. Silicon dioxide is the sand that you used the other day in lab. Was it a liquid? No. Was it low boiling? No. Does it dissolve in water? No. Was it a gas? No. It's sand. So the actual structure of silicon dioxide it's a network. And a network is something that keeps going and going and going and going. If it's any kind of network, if you're in a network, it just kind of keeps on going. And that's what sand is. And salt, it's like that too, but salt is ionic. This is covalent. So every single oxygen is bonded to 2 silicons, but every silicon is bonded to 4 oxygens. It ends up being a ratio of 1 to 2. It's dirt, quartz, it's amethyst. There are silicates in a lot of things. The red clay that's outside, all over Surrey County. Clay also is silicon dioxide, has a lot more iron content, that's why it's red. But the reason it's kind of slippery is because it's not as big of a network that goes out, it's more of sheets. And so they just kind of slide, they can slide past each other, so it's more slippery. So that's and that's why we can't draw it, because there's no way to, you can't really, there's no simple way to draw a network. So ratios, we can't draw as simply. A molecule, everything is there and it has an end. And so the practice problems, we're going to do the first few together. I found some common substances, and I'll tell you what the substances are once we've gone through the examples. Okay, so I want you to be able to look at any size molecule. So this is a structural formula, right? Because it has bonds and it shows the elements and it shows the arrangement. Every element is there for you to count. So how do you figure out what the molecular formula is? The molecular formula is just the chemical formula of a molecule. So if it's a molecule and it's a chemical formula, it's called a molecular formula. So how do we figure out the molecular formula? We just count. So the first thing you want to do is look at the structure that you see and see what elements are there. So if you look all over, you can see several element symbols, but you're only going to list each element symbol one time to do the molecular formula. And so what elements are here? Carbon, hydrogen, and oxygen. And then you want to somehow systematically count each one of those. Don't try to count them all at the same time. You can do the easiest one, which to me is oxygen. But then you got to find a systematic way to do all the hydrogens and carbon. Okay? So if you look at it, how many oxygens are there? There's two, yeah. There's one right here, and that's an oxygen too. It's kind of hard to see because of how much I've had to blow it up here. Okay, so to write that portion of the formula, you used a subscript of 2 behind the oxygen. So we got the oxygen portion. I'm going to do the carbon next, and this is not the way that you would think to do the carbon, but if you see this is a ring because the carbons are in kind of like a circle or a hexagon shape. If you see a ring in the molecule that you're looking at, the easiest place to start is to count the ring and then count the pieces that are off the ring. If you try to go left to right, then you're going to hit the ring, and then what do? You lose track of where you were. And so if you just count the ring and then count this piece and then count that piece, it's actually much easier. But it doesn't seem, it's not, I don't think it'd be what you would automatically think of because we were used to reading left to right. So if you do it that way, if you count the center part that has the ring here, there's a carbon at every corner, and this is a hexagon. So guess how many carbons there are? There's 6 of them here. And then this carbon is bonded to this one. So we've already counted this one, but we haven't counted these. And so how many carbons are there over here? There's 4. Now, you might think that 3 goes with carbon, but it always goes after what the symbol is. So it's after the hydrogen, so that's 3 hydrogens. And so there's 1, 2, 3, 4 carbons. So there's 4 there, and then there's 6, that makes 10. And then you go to this portion up here, and there's 1, 2, 3. So there are a total of 13 carbons. Does that make sense? And to me, that's much easier to keep track of what you're doing than to start, because if you start down here, then you got to go there and back and there, and then you got to go around and wait a minute, you go here and then come back, and it's just crazy. Okay. Or if you print it, you can check them off. You can go 1, 2, 3, 4, and then just keep checking off, and then hope nobody talks to you while you're doing that. Okay, hydrogen. This is the one that's more difficult because there's so many of them. So again, you want to kind of just some way to figure out the hydrogens. So there's 1, 2, 3, 4 here, and then there's 3 and 3, so that makes 10, 11, 12, 13. So everything over here, that's 13. And in this portion, 14, 15, and then 3 more is 18. This is one of those things that if you are counting that high, you want to count more than one time. Or work with somebody and you count and them count and see if you get the same number. Okay, so that is the molecular formula. So we're going to do the same thing for the next one, and then I'll talk about molar mass. Okay, so the next one. Same 3 elements, but a completely different compound. So we've got carbon and hydrogen and oxygen. And again, you just want some kind of format. They're all equally about the same to count these. So if you just count carbon first, because this just like goes straight down the chain. How many carbons? there's 6 carbons. And then hydrogen, there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then oxygen, 1, 2, 3, 4, 5, 6. There's 1 oxygen on every carbon. C6H12O6. This molecule here is fructose. It is a monosaccharide. It's not glucose. It looks kind of like glucose. Or if you saw C6H12O6, you might think, oh, glucose. But glucose is not the only monosaccharide with that formula. What makes the monosaccharides different from each other is where this oxygen, this double bonded is. And then also, the way that this oxygen is pointed and that oxygen is pointed also makes them different. So glucose and galactose, they look identical. You would think they were, but like one of the OHs is pointed the opposite way, and it makes it a different sugar. Okay, so right next to it I have molar mass. So, what is molar mass? Molar mass is a conversion factor, and it is the #1 conversion factor that we do. And I'll write down a good definition in a minute, okay? I'm just going to show you how we calculate it, and then we'll talk about what it means. The way that you figure out what's called the molar mass is we use these atomic masses that we've been talking about. And we add in the weight of every atom that's up there. And so what you want is you want the actual molecular formula so you know how many times to add carbon in. So guess how many times you add carbon in? 13 times. Why? Because there's 13 of them in the formula. So what you do, this is the number portion of molar mass, and we'll go over the meaning of it in just a minute. You take the subscript, which is how many of the element there are in the formula. So you go 13. And you multiply by its atomic mass. And so we're going to use all of the digits in the table, and I want you to use the table that I gave you. And so you're going to use 12.011. And molar mass, the unit for mass is in grams, because everything's been scaled up to what's called a mole. And so it's the weight of the element in grams. So that's for carbon. So what would we do for hydrogen? 18. And then we do times its atomic mass, which is 1.0079 grams, and that's for the hydrogen. And then we add in 2 times 15.999 grams of. You're going to add those numbers together, and the total is the molar mass of this formula here. And we're not going to round or anything, so it's 13 times 12.011 plus 18 times 1.0079 plus 2 times 15.999 equals 206.2832, and that's grams, and it's of the whole formula. And that equals 1 mole of the whole thing. So the molar mass would be its atomic mass in grams. And that equals 1 mole, this new unit that we're going to go over, mole, So it ends up being a conversion factor. Okay? So I want you to do the same thing for the fructose.